Let's march through a couple of issues around our understanding of the brain. We've talked a lot about the mind, and we've talked about quantum physics, and we've talked about consciousness. I want to continue with some of what was talked about earlier today around how we think about the brain itself. And let's start with what we might call myths. And the first one being that you only use 10% of your brain, something that was perpetuated in this Hollywood blockbuster from earlier this summer, Lucy. And you can see that over the face of Scarlett Johansson. It may be actually the case that we only understand about 10% of what we need to about the brain, but in fact, the data that we have currently would say that the cortex is basically always on. We've got a very active cortex, perhaps most active actually when we're not thinking about anything specifically. The brain is the most metabolically active organ in the body. Even though it's only about 2% of our weight, it's 20% of our oxygen consumption. So it's essentially taking 10 times more energy than you would expect by weight alone. And as I just said, its activity is intense at any given time. It's basically fully on at 100% as far as we can tell. And if anything, what neuroscientists call the task-positive state, when you're asked to focus, and when you have a task, the cortex, general cortical activity goes down, not up, which is not the spirit of what the movie was about. But even though we have this sense that we've got a cortex that's always on, it's important to realize that with that 100% activity, there's still enormous opportunities for rewiring, for plasticity, for adapting to changing environments. And the brain, in ways that I'll talk about a little bit more in a minute, seems to have this capacity to do things that we simply can't quite understand how it does it. But it does it in spite of having this very high metabolic load. Second myth is that we have two brains inside us, and it's one of the most common things you hear about, the right brain, left brain dichotomy. You could say it's the scientists versus the sages, but in fact, that's, as far as we know, really not the way the brain normally works. The hemispheres are incredibly well synergized and tightly wired together. There's an enormous bridge called the corpus callosum that links together the two hemispheres, and it's almost always the case when you look at activity for anything that the brain is engaged in. If you see it on the right, you're going to see it on the left in what we would call the contralateral area. That is the same part of the brain on the opposite hemisphere. It is true that when there is damage, if you cut the corpus callosum and you separate the two hemispheres, you can get these very specialized functions between the two, but it's not the case that that's the way the brain actually works. So, as far as we can tell, the way the brain works is actually to ensure that those two hemispheres are working together in a way that they need to. We've talked a little bit at this meeting about brain imaging, and you've seen some beautiful images of fMRI, functional magnetic resonance imaging. We talked about this yesterday and a bit this morning. And it's important to recognize that even though fMRI is one of the tools we have today to understand what's going on in any given part of the brain, so it's no longer the black box it used to be, it also can be very misleading. What you're seeing with fMRI is not what the brain is doing in a particular moment. You're seeing changes in blood flow. And those changes take a while. They take about 2 or 3 minutes after the event has actually happened. So fMRI doesn't capture brain activity at the speed of thought. It captures brain activity at the speed of blood flow, which is much, much slower. There's always a long latency. And of course, it doesn't have the kind of precision in space or time that you'd want, because every, what we would call voxel, every spot, the smallest spot you could get that would light up on an MRI scan, represents hundreds of thousands of cells of many, many different types. So it's a rather gross measurement of what's happening locally. It happens to be the best we've got, but it's certainly not, for all intents and purposes, a precise readout of what's happening at the cellular level, which is where we think so much activity is probably really taking place. There are also problems in many of the studies that you see, and these are always in the media at this point, and they make fabulous images. We sometimes call it sort of high-tech phrenology because these are such beautiful images. But you should recognize that those images are the composite of a large group of people who are put together and doing really profound statistical manipulations to be able to get the differences that you see. Often they are really tiny, tiny differences in blood flow, but magnified across many, many people, you can begin to see a signal against much of the noise. So it's not as if what you're seeing represents the activity of any one individual. In fact, we haven't figured out yet how to use fMRI for any individual, for instance, to produce a biomarker, which is something we'd be interested in. And it's also obvious that, maybe not so obvious, but that if you see what we call activation, if an area lights up, well, we tend to think that that means that area must be engaged and it must be active in whatever behavior we're interested in. It's also possible that what's lighting up are inhibitory cells, inhibitory circuits that may be actually turning down in terms of physiological activity, though blood flow is increasing in that area. So for all of these reasons, be wary when you see fMRI data. It's very interesting, and it points in a particular direction. It's all correlational. You heard yesterday from Bob Thurman about the importance of thinking about causal relations, not just correlational ones. This is a technique that doesn't get at cause, it really gets at correlation. Much of this was summarized in I think, a really interesting book, which I would recommend, called Brainwashed, which is really quite critical of much of what you see today in the fMRI literature. And it helps us, I think, to take a little bit more sober look at many of the studies being done. Still very interesting. It's the tool we've got to work with today, but it's not where we need to be. I couldn't resist from putting in this as a myth, the fact that in my institute, which is the National Institute of Mental Health, we deal with mental illnesses, mental disorders, and the language has really constrained us here, because though we call these mental disorders, increasingly we think about them as brain disorders, that all of these, whether it's autism, attention deficit, hyperactivity, depression, bipolar, schizophrenia, it's a long list, can now be understood in terms of brain circuitry. And we begin to think about them now not as having just a chemical imbalance. We don't talk about depression any longer as being a quart low in serotonin. It's much more important to think about these as actual circuit disorders, the way you would think about a conduction defect in the heart or a problem in any part of neurology where you have a circuit that's not functioning in the way you want it to. The reason why that's important is that it points us towards treatments that may not simply be trying to alter chemical balance, but treatments that are thinking about the circuitry itself and how do we tune those circuits. And if you just step back and consider that for a moment, you begin to realize that if you want to tune a circuit, it may be better to do that through a cognitive intervention or through something that actually engages that specific circuit rather than pouring something into the brain that's going to affect hundreds of thousands of different circuits that you probably don't want to influence. This is really critical here because we're talking about a group of disorders which I think have been grossly misunderstood and grossly mistreated, and yet they are the #1 source of disability in the United States. That's always striking to people who think about cancer, heart disease, and all of these other illnesses being so much more costly and disabling. In fact, the data tell us something quite different. And the reason why these are, out of 291 diseases and injuries, why this group of disorders has now emerged as the leading source of disability is because they start early in life. 75% of people with mental disorder describe onset before age 25, which is, of course, very different from the data with cancer or heart disease or stroke. Finally, one last myth, and that is the problem we have in even talking about the brain, because we always try to put it into terms that relate it to something we understand much better. It is indeed a profound mystery, and like any mystery, the way we try to get our arms around it is to say it's like And in this case, it is like a computer, a muscle, a musical instrument, which is actually kind of a nice analogy in some ways. It's a chemical black box which has various things sloshing around in it. And the point I want to leave you with in thinking about these myths is that we actually don't know what the brain is like. It's not really any of those things. And we constrain ourselves every time we put it into the context of those kinds of metaphors, because the brain may be different from anything that we currently understand. I can't resist from sharing this oft-quoted statement that if our brains were simple enough for us to understand, we'd be too simple to understand them, but that begins to capture the difficulty of what we're dealing with. And let me just quickly tell you that the complexity here is truly mind-boggling. 3 pounds of matter, 86 billion cells, each cell having at least 1,000 connections. So you're talking about 100 trillion or more synapses. These are real numbers after a while. These are really big numbers. And just the connections between them would get you halfway to the moon, 100,000 miles. That's a pretty extraordinary set of numbers to deal with. The complexity is indeed mind-boggling. So the problem we have to face is, how do we break through that? How do we begin to understand this most complex organ? We have a very deep understanding currently of the heart, of the kidney, of liver, and we have a very, very poor understanding of how the brain works. I want to share with you a quote that I've found very helpful in thinking about this, and it actually comes from a very different area, which is astrophysics. So this is now the search for outer space. Freeman Dyson, astrophysicist at Harvard, who said that new directions in science are launched by new tools much more often than by new concepts. Now, for many people, that seems a little bit counterintuitive because we're so in love with our ideas and our concepts, but certainly you can get a sense of that in the world of astronomy, where having a better telescope allows you to see farther and to see more than you could. And as he says here, the effect of a concept-driven revolution is to explain old things in new ways, but the effect of a tool-driven revolution is to discover new things that have to be explained. Now, that's an extraordinary ambition, and it's a real possibility here where we're dealing with a very complex problem, perhaps more complex than the cosmos in so many ways, which is the problem he's dealing with. We're fortunate that we have this new project that I mentioned before, launched by President Obama in April of 2013 in the East Room of the White House, where he said that he wanted to see this next great American project, thinking about the effort to land a man on the moon and to explore outer space as one of the previous American projects. It was time to go to inner space. And as he said, borrowing from the same way that Freeman Dyson was thinking about this, if we're going to make the progress we need here, and you heard from Dr. Black earlier today, how important it's going to be to make progress against Alzheimer's disease. And to do that, we've got to get that understanding we don't have. And to get the understanding, as President Obama said, is we need to give scientists the tools they're going to need to get a dynamic picture of the brain in action. It's about the tools. So I want to take just a few minutes to run you through why this may be the time to do this. He's called for an all-hands-on-deck effort with many different agencies of the federal government working with a series of private partners, and all of a sudden we've got projects now not only in the US, but in the EU, in Israel, China, Japan, and Australia, and there'll be others happening as well. This is becoming a global effort to try to explore inner space in a way that we've never been able to do before. This is the time to do it, not only because of the public health mandate, but because of the progress we've had recently with the tools that have already emerged. Brainbow from Jeff Lichtman and Josh Saines at Harvard, an extraordinary ability to use fluorescent probes for the first time to disentangle complex areas of the brain so you can see individual cells and their projections. A new technique developed by an engineer working with a neuroscientist at Stanford, Carl Deiseroth, and his colleagues have taken the brain, this is a mouse brain you see on one side of the screen, and in the middle, the same brain has had all of its fat removed, so it's now transparent, and the fat has been replaced by a hydrogel, And what you see in the last screen there, and the green brain is the same brain under a fluorescent microscope. You can see it's still intact, and the result is that the brain has kept its entire three-dimensional integrity, but now it's transparent. You have a transparent brain, which means that you can look into the brain with a microscope, and now we have new fantastic microscopes to do this, and you can begin to travel through it and for the first time see the cells and their relationships to each other and all of their projections and how they're arrayed in such a way that you can explore, just as if you were doing this through computer animation. But this is not computer animation. This isn't a model. This is a real, in this case, mouse brain. It allows you to fly through and then to fly out. And what you're doing here is you're moving around to the front of the brain. That's the olfactory bulb. Put on your seatbelt. We're going to move right through it and take a dive where you'll be able to actually see the relationship of not only the olfactory bulb and the amygdala and the hippocampus, which is coming up on the right, but then it'll take us right back out through the cortex. And you can see these cells beautifully arrayed to be able to see their relationship and their projections to each other, giving us a picture of how the architecture of the brain actually is arrayed. And what we really are after, of course, is to get the language of the brain, to be able to read the language of the brain at the speed of thought. And how do we do that? We can't do it yet with fMRI, but this technique developed by Mark Schnitzer, also at Stanford, with Carl Deiseroth, is a way of labeling the brain so that every time a cell fires, it lights up. And then Mark, who's an engineer, has created a new generation of microscopes that are absolutely tiny. They're micro microscopes. You can insert them right into the brain. And you can begin to look at any area of the brain you think is involved in any behavior you're interested in. So in this case, he has a mouse with a microscope implanted in its brain that's walking around in this 8-arm maze, which you see in the middle. And on the right, in the far right panel, you see those cells firing. And so Mark and his colleagues have said, can we take that pattern of firing and break the code? Can we figure out from the cells that are firing the place and the space where the mouse is at any given moment? And they're pretty good at it. They can do this within about 1 mouse length just by looking at the code of those cells firing in the hippocampus, one part of the brain that's important for place and space. What about humans? Well, we've got a new project called the Human Connectome Project that's bringing lots of different kinds of imaging together to get a new picture of the brain. With the tools that we now have, we can, for the first time, get the wiring diagram of the human brain in a way that we couldn't before. This beautiful image from the group at Mass General Hospital in Boston has begun to show us how to even follow fibers when they're crossing. And we've begun to actually now look at brain activity in humans with a much higher resolution than we've had before. One of the things that will really kick off this brain initiative is this ability to follow the different parts of the brain, the cortex, and watch them fire in real time in extraordinary ways. We've got now these areas of the brain connected in ways we really didn't even know about before. So to finish up, what we're talking about here is mapping the circuits, measuring the activity, both electrical and chemical, in a variety of ways, to understand how the brain generates thoughts and actions. Our most complex organ, but we actually know very, very little about it, except something about its complexity. We've got some new tools, and now the question I think in front of us is whether by mapping the brain in this way, we'll be able to get new insights into the mind, into consciousness, into the things we've been talking about for the last day or so. Will we be able to actually figure out what is consciousness, what it means to be unconscious, and pretty soon, I think, we'll have answers for that. You'll just have to stay tuned. Thank you very much.
So before I ask you my question, we should tell them we have a long history.
Oh, this is, I probably know Deepak longer than anybody in the room. Is that possible?
Other than my wife, yeah.
I would hope so. I hope she knows you better.
Yeah.
I was a medical student in Boston at the Boston VA hospital, very close to dropping out of school because I was really pretty discouraged by the kind of care that you happened to mention earlier this morning. And Deepak was my resident 2 years ahead, and a very good physician.
Yeah, I still am. What do you mean? Okay.
So when somebody asked me about that today, and when I said, you know, Deepak was different in those days. And I didn't mean different from the way you are now, but I meant different from everybody around us. And they said, well, how do you mean? And I said, he had a level of compassion that no one else showed at the VA.
That's beautiful.
So,
thank you. Thank you, Tom. So I have just one question based on your very brilliant talk and, you know, President Obama's commitment and now the Allen Institute and the whole European collaboration on the connectome. And you started off by saying these are circuits, right? And isn't the connectome almost infinitely dynamic? If I tell you to think now of, say, your mother or your home or the last paper you published, your whole connectome is going to have to shift. I think connectome of a musician may be different than, say, an acrobat, but that's just about it. The rest, the connectome is probably shifting by the second, or am I wrong?
So you want to think about connectomes in two ways, structure and function. Structure at the level that we can measure is fairly static and difficult to shift around, although it will shift with experience. But function is always moving, and it's incredibly dynamic on a moment-to-moment basis. It is really the speed of thought that we're trying to capture here. We don't have the tools we need to do. We actually are getting those tools for flies and fish and now for mice, but what we don't have is the ability to do that in humans. And I think for us, the real challenge will be to capture exactly what you said, to capture the dynamic nature of how the brain is working, and to be able to both monitor that and then to think about how whatever we provide in the way of experience begins to alter that.
Thank you, Tom.
Thank you. But even though we have this sense that we've got a cortex that's always on, it's important to realize that with that 100% activity, there's still enormous opportunities for rewiring, for plasticity, for adapting to changing environments. And the brain, in ways that I'll talk about a little bit more in a minute, seems to have this capacity to do things that we simply can't quite understand how it does. Myths. And the first one being that you only use 10% of your brain, something that was perpetuated in this Hollywood blockbuster from earlier this summer, Lucy. And you can see that over the face of Scarlett Johansson. It may be actually the case that we only understand about 10% of what we need to about the brain, but in fact, the data that we have currently would say that the cortex is basically always on. We've got a very active cortex, perhaps most active actually when we're not thinking about anything specifically. The brain is the most metabolically active organ in the body. Even though it's only about 2% of our weight, it's 20% of our oxygen consumption. So it's essentially taking 10 times more energy than you would expect by weight alone. Let's march through a couple of issues around our understanding of the brain. We've talked a lot about the mind, and we've talked about quantum physics, and we've talked about consciousness. I want to continue with some of what was talked about earlier today around how we think about the brain itself. And let's start with what we might call, and as I just said, its activity is intense at any given time. It's basically fully on at 100% as far as we can tell. And if anything, what neuroscientists call the task-positive state, when you're asked to focus, and when you have a task, the cortex, general cortical activity goes down, not up, which is not the spirit of what the movie was about.